In the previous video, we introduced electron configuration and the division of the periodic table into blocks. Today, we continue our discussion of the before-mentioned topics. We've already defined electron configuration as the methods by which we describe the positions of electrons in an atom. We also talked about the threefold hierarchy of electron positioning. Shells or energy levels contain subshells, and these subshells contain electrons. Long-form notation is the standard method of showing electron configuration, and writing a configuration for an element in long-form notation consists of writing one or more terms, each with two numbers and one letter. The number on the left represents the energy level the subshell is located in. The letter tells us the type or shape of the subshell, and the exponent represents the number of electrons in said subshell. Finally, we talked about the division of the periodic table into 4 blocks based on which subshell type a particular atom's valence electrons can be found in. The long-form notation of electron configuration, which we discussed last time, is but one of 3 methods, and today we will introduce the other 2. We begin with the shorthand or noble gas notation, and once we've covered that, we will get into orbital diagrams. Now, the purpose of shorthand notation is pretty self-explanatory. We want a shortcut for showing electron configurations. Writing out the long-form notation for an element without too many electrons, oxygen for example, is a simple thing. But once we start looking at elements whose atoms have many shells and hundreds of electrons, the long-form notation becomes rather tedious. We can circumvent this drudgery by substituting a noble gas configuration into the long-form notation of another element. A more detailed explanation of this is incoming, but first, let's take a moment and remember our cast of characters. The noble gases, if we recall from previous videos, are the non-reactive gaseous elements found in group 18 of the periodic table. They are, in order of increasing atomic number, helium, neon, argon, krypton, xenon, and radon. Their element symbols are provided here in our notes. We'll want to remember these noble gases and their corresponding symbols as we move forward. Also, all the noble gases exclusive of helium are in the p block, so all of their electron configuration should end with a p subshell. Helium, meanwhile, is in the s block, as confirmed by its configuration 1s2. The best way to explain the shortcut behind shorthand notation is to look at an example. Here we have the long-form electron configuration for aluminum. Aluminum has an atomic number of 13, and its long-form configuration is 1s2, 2s2, 2p6, 3s2, and 3p1. Moving on, let's look at the long-form electron configuration of the noble gas neon. Neon has 10 electrons and a long-form configuration of 1s2, 2s2, 2p6. When looking at these two configurations side by side, it will be immediately apparent that the 3 terms of neon's electron configuration are exactly the same as the first 3 terms of aluminum's configuration. In the previous video, we actually did 2 example problems on long-form notation in which we wrote the configuration for oxygen and then the configuration for calcium. There, I mentioned that it's possible to shortcut our way through writing calcium's configuration by simply copying oxygen's configuration, because oxygen has fewer electrons than calcium. All we need to do was change the exponent on a single term and then continue from there. In other words, the first few subshells of a calcium atom will be filled with electrons in almost the same arrangement as an oxygen atom. Shorthand notation uses this notion to provide us with a shortcut for all elements. However, it's crucial to remember one point. We can only use shorthand notation with noble gases. Down below, we have our finished shorthand notation configuration for aluminum. First, we have the long-form notation for aluminum, and underneath it we have the long-form notation for neon. The matching terms are written in green. What we can do here is substitute the element symbol for neon, or Ne, into the configuration for aluminum where those terms in green used to be. The noble gas's element symbol always goes in brackets, by the way. After closing the brackets, we simply add on the extra subshells that aluminum has and neon lacks to obtain the shorthand configuration for aluminum. It's only necessary to remember 2 basic pointers before doing shorthand notation configurations. Firstly, we can only use noble gases for shorthand notation. Do not put any other element symbols in brackets. Only helium, neon, argon, krypton, xenon, and radon are allowed. Secondly, We have to remember to use the noble gas from the row or period above the element we're writing the shorthand notation for. Another way of saying this is to say that we have to use the noble gas that has the closest atomic number to the element in question. The noble gas we choose has to have fewer electrons and therefore a lower atomic number than the element we're writing the shorthand for. In our previous example, aluminum is in period 3 on the periodic table, and neon is in period 2. Neon has 10 electrons per its atomic number, whereas aluminum has 13. It wouldn't make sense to use argon, which is in period 3 and has 18 electrons, in the shorthand notation for aluminum, because argon has more electrons than aluminum does. We also wouldn't use helium in the shorthand for aluminum, since helium only has 2 electrons while neon has 10. Out of all the noble gases, neon has the closest atomic number to aluminum while also having fewer electrons. From our video on periodic trends, remember that atomic number increases going both left to right and from top to bottom. This should be useful in finding the right noble gas to use when writing configurations in shorthand notation. Alright, let's do an example problem. Example 1 would like us to write the shorthand electron configuration for sulfur. Go ahead and pause the video if you'd like to try this one yourself, but before you do, be sure to grab a copy of the periodic table and one of our snake diagram. They'll come in handy here. Our first step is to find sulfur on our periodic table and write down its atomic number. Which is 16. There we are. Our second step is to write the long-form electron configuration for sulfur. To save time, I'm not going to go over how to find the long-form configuration, so if you're a bit lost, be sure to go back and watch Unit 1 Video 4. For everyone who's still here, the long-form notation of sulfur is as follows. 1s2, 2s2, 2p6, 3s2, 3p4. Excellent. Our third step is to find the noble gas that has the next smallest atomic number as sulfur, or alternatively, we can look at the noble gas in the period directly above sulfur. In either case, we find that the noble gas to use in this example is neon, which again has 10 electrons, and if we remember from a few minutes ago, it has a long-form configuration of 1s2, 2s2, 2p6. So, the only subshells of sulfur that don't match the long-form configuration of neon are 3s and 3p. In the end, all we need to do is write the symbol for neon, or Ne, in brackets, and then write 3s2, 3p4 next to it, like so. And that right there is the shorthand configuration for sulfur. Let's do another. Example 2 wants us to write the shorthand configuration for iodine. First, the atomic number. Iodine has an atomic number of 53. This is where shorthand notation really starts to come in handy, since I doubt anyone truly wants to write out the long-form notation for an element with 53 electrons more than once. Necessity might be the mother of invention, but laziness might very well be the father. Now, let's follow the steps from our previous example. First, the long-form configuration. For iodine, the long-form configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4d10, 5s2, 5p5. Next, we find the correct noble gas. Iodine is in period 5, and the noble gas in period 4 is krypton. The long-form configuration of krypton is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6. I know the ordering of subshells doesn't line up perfectly on this one, but the method is the same. We write the symbol Kr in brackets and then fill out the remaining subshells to make Kr 4d10, 5s2, 5p5. That concludes our discussion of shorthand notation. Next, let's talk about orbital diagrams. An orbital diagram is a visual representation of the spin of electrons in an atom. We stressed last time that electrons are three-dimensional particles, which means that they can move in opposite directions, as we will see soon enough. We also previously introduced Pauli's exclusion principle, which tells us that 2 electrons are the maximum number that can fit in any orbital path. It's important to emphasize this point right here. We're not talking about energy levels or subshells here. We're only talking about the paths electrons take inside their subshells. A subshell can have more than 2 electrons, certainly, but only 2 electrons follow the exact same path at any given time. Once again, the best way to illustrate this is to provide an example. Here we have the orbital diagram for the element helium. As we can see, the diagram itself consists of a box with 2 arrows inside it, one upward-facing arrow and one downward-facing arrow. The box is labeled 1s, which corresponds to the subshell involved. In this diagram, each arrow represents a single electron, and the arrows are facing in opposite directions to show the difference in spin direction. Helium has 2 electrons, which makes this diagram a complete representation of its electron configuration, only instead of using letters and numbers, we're using boxes and arrows. That's all an orbital diagram is, really, a pictographic way to show electron configurations. Point 14 here gives us the final rule we're going to borrow from quantum chemistry. Hund's rule says that for subshells with more than one box, we'll explain this further in a minute, electrons will fill empty boxes first before pairing up. Put simply, electrons are introverted. Let's see Hund's rule in action. This is the orbital diagram for nitrogen, which has an atomic number of 7. The long-form electron configuration for nitrogen is 1s2, 2s2, 2p3. Down here, we have 2 orbital diagrams for nitrogen. Both represent the 3 subshells and both show 7 arrows in total. Also, because the 2p subshell can hold a maximum of 6 electrons according to our snake diagram, there are 3 interconnected boxes above the label 2p. In the correctly drawn orbital diagram, the 3 electrons nitrogen has in its 2p subshell are divided amongst the 3 boxes, one upward-facing arrow in each. The incorrectly drawn diagram, by contrast, places the first 2 arrows in the first box, the remaining arrow in the second box, and leaves the third box empty. We don't want to do this. Electrons like to spread out, and when an extra box is available, they will take that box. To help make this clearer, we can imagine these boxes as houses, the electrons as people, and the subshells labeled as street names. Nitrogen has 3 electrons that all want to live on 2p street. 2p street has 3 empty houses available. Because the electrons are introverts, they would rather not move in with each other when they can each live alone and have their own space. So they're each going to take one house for themselves instead of moving in together and leaving one house unoccupied. A few pointers for drawing orbital diagrams. Firstly, when it comes to drawing the boxes, or houses if you will, we can find the number of houses to draw by having the maximum number of electrons that can fit in that subshell. For example, the subshell 2p can have a maximum of 6 electrons as denoted by the exponent. 1/2 of 6 equals 3, so we draw 3 boxes and label them all 2p. Secondly, whenever we apply Hund's rule and separate the introverted electrons into separate houses, it doesn't matter if the lone arrows are upward or downward facing. What does matter is that we keep them consistent. For our correctly drawn example for nitrogen, for instance, we made sure to draw all the solitary electrons on street 2p as having the same direction. We could have easily made all these 3 arrows downward facing, and that wouldn't pose any kind of problem, but it is important to stay consistent. We don't want to draw one up arrow and two down arrows or something like that. Thirdly, the best way to make sure we draw the correct orbital diagram is to write out the long-form electron configuration of the element first, before doing any drawing whatsoever. Let's put our knowledge of orbital diagrams into practice. Example 3 would like us to draw an orbital diagram for oxygen. You can either pause the video and do this problem yourself, or we can do it together. Before we do anything else, let's write out the long-form configuration for oxygen, which has an atomic number of 8. 1s2, 2s2, 2p4. Now we can start drawing our boxes. But how do we know how many boxes to draw for each of these subshells? We use our first pointer and half the maximum number of electrons each subshell can hold. For 1s, half of 2 is 1, so we draw 1 box. For 2s, it's the same. For 2p, the maximum exponent value is 6, not 4, and half of 6 is 3, so we draw 3 boxes. I do realize I'm harping on about this a little bit, but drawing the wrong number of boxes is probably the most common mistake made when drawing orbital diagrams. Once we add our arrows, we have the complete orbital diagram for oxygen. Here's something a bit more complicated. Example 4 says, draw an orbital diagram for vanadium, abbreviated V. The atomic number of vanadium is 23, and its long-form electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. Now that we have this information written down, we can start drawing our boxes. Remember, the number of boxes for each subshell is given by having the maximum number of electrons that can fit in said subshell. The only subshell that gives us trouble is 3d, since the 3d subshell can actually hold a maximum of 10 electrons. This is why it's important to look at a snake diagram instead of simply glancing at vanadium's electron configuration. It's a pretty easy mistake to make, looking at the electron configuration and assuming that the 3d subshell has an exponent of 3 and can therefore only hold 3 electrons. But this is of course not correct. We actually need to draw 5 houses on 3d street. Having done that, all that's left to do is fill in the arrows. For the sake of illustrating our earlier point, let's draw all the solitary arrows on 3d street as downward facing arrows. Again, we could make all these upward facing instead if we wanted to. It doesn't matter. Consistency is what's important here. And there we have it, the orbital diagram for vanadium, consistent with Hund's rule and our pointers from earlier. As a closing aside, looking at orbital diagrams actually gives us another insight into why noble gases are as non-reactive as they are. Here, we have the orbital diagram for neon, which has an atomic number and electron configuration we've already discussed several times today. As we can see, neon's orbital diagram shows boxes that are completely filled with arrows. In other words, there's no more room for new electrons to move in. All the houses on every street in neon's neighborhood are filled to capacity, so neon doesn't need to go out and find new tenants. That concludes our study of electron configurations and orbital diagrams. In the next video, Unit 1, Video 6, we will be talking about isotopes and hopefully closing out our first unit. Thank you for watching.